This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Well, welcome everybody. It is so good to join with you together on this Wednesday, January 15th. And as we look at lesson 19 and open shapes. I'm going to drag people to the middle of my screen here so I can see you all. We are moving into the third dimension today. So as we look here at our screen, we're here on lesson 19, and we are in the third dimension now. And we call that astronomy and human space. So that astronomy is a nod to the quadrivium. So, we have arithmetic, which is numbers, geometry, which is our shapes, and then astronomy is putting our shapes into motion, and then harmonics are numbers into motion. But we also think of that astronomy as giving us, right, our whole cosmos. So when we think of human space, that idea that we aren't just here on Earth, but God created the heavens and the earth. And so that astronomy is a nod to that, as well as to the quadrivium. Just a reminder that we are using the complex materials, but we encourage you to use the domain that is most appropriate to you and your students on your mathematical journey. So as we enter into our time of exordium here, what more appropriate number for 3D than 3? So why did I choose this number? I may have just given it away.
You like the tie-ins with the dimensions, I'm assuming.
It did feel like a natural number to pick today. There's another hint. What kind of number is it?
Prime.
It is prime.
Odd.
Odd. What else do you know?
It represents like the Trinity idea.
It's a very meaningful number, isn't it, Nina? Especially when we think of the Trinity and all the threes that we see in the Bible.
Mm-hmm.
I don't know how significant, but it's a natural number.
It is a natural number. That is significant.
Okay.
What other number sets could it belong to if it's a natural number?
It could be an integer.
Mm-hmm.
A rational number.
A rational number.
I mean, it could even be complex, right? Because complex encompasses all of those, right?
Yeah. There's one more set that we generally talk about between rational and complex.
Real.
The reals, yeah. Is it a big number or a small number?
I would say it's small compared to last week's 2020. Was last week 2025 or was it the week before?
Last week was,
last week.
Yes.
Okay, yeah.
Yeah, I was going to say it depends on where you're looking on the number line, if it's small or big, sort of relative. And I would never have said that before.
What are some of the threes in the Bible besides the Trinity? Where else do we see?
I just thought Meshach, Shadrach, and Abednego.
Good. Yeah.
I don't know why they came to mind.
And I thought of Hebrews, not Hebrew, 1 Corinthians 13. It says that there is faith, charity, hope, faith, hope, and charity. And the greatest of these is, anyway, those three.
They talk about the 3 days for the miracle of, like when Jonah's in the whale for 3 days, and then that's referred to in the Gospels.
Yeah. Because the other 3 days is Jesus, right? Between the cross and resurrection. Good. The cord of 3 strands isn't easily broken. There's a lot of it's kind of amazing, isn't it? Because we probably tend to think of 3 as being, it's a insignificant, right? It's a common number. We count to 3 all the time, right? Don't make me count to 3. Um, all of those things. But there's a lot about 3 that we could talk about, right? When we think about triangles are this foundational shape in engineering and physics, as well as in geometry, right? How many points determine a plane? 3, right? That's why a stool with 3 legs will never teeter-totter. So it may not always be parallel to the ground, but it won't ever wobble if it has 3 legs, because it will always lie in one plane. So yeah, so we could probably go on and talk about 3 for a long time. Right? What base would I talk about 3? What bases do not have that numeral for 3? How about that? Going way back to lesson 2.
Base 2.
Base 2 and
Base 3 also does not have a 3, right?
very good, right? So once we get to base 4, we start using the numeral 3. So it's our first odd prime number. Great.
3 makes me think now of indices, and we were just reviewing in class on Monday with lesson 17 why MathMap uses GEMA and AMEG instead of PEMDAS, and now I'll forever think with the indices of the trio.
That's great. Yeah. Yeah, there's a lot. I mean, I think probably we could have a whole conversation, all like our entire hour, just talking about the number 3, which is pretty powerful when you think about it, right? Because there's so much that we could say, and it's just one little number. But let's go ahead and take a look at our cover today. And I'm just going to start off with, does anybody have any idea why this picture may have been chosen?
Well, flowers come from a bud that opens. I mean, these do.
Yeah, that's excellent, Jill. That's right. So the art was chosen because that we wanted that idea of blooming, of opening, right? That we see with the flowers there.
I always think of butterflies as like the super transformational, like the symbol of all things transformational, right? Because it starts out looking like something completely different than it ends up looking like. And there is this process that happens where the caterpillar really kind of dies, right? Kind of in a tomb, so to speak, and then emerges as something that's completely transformed. And so I'm gonna guess. Now yours says open shapes, but mine says transformations. Am I looking at the wrong week?
I was gonna say, are you looking at lesson 19?
Oh, I'm sorry. I'm looking at 18. I thought we were doing 18 today. Okay, sorry.
No, but it's still that idea of this opening, right? And I love that you're reminding us of what we talked about last week when we talked about things transforming, right? Because when we think moving into 3D, we can see a whole different dimension of transformation, right? And so one of the things that, taking what Nicole's pointing out with these, what we looked at last week, we looked at all of these um, functions, especially that were in 2D. And I want you to take a minute now and think about if I had a line, right? So I've got a line in 2D, right? And so all we can see is that line. If we could somehow open that up, right? And so now we see that in 3D, what would we be looking at? If I could somehow take, right? So you're looking at that, and if I could sort of line, I'm going to try and see if I can make this happen, right? So here, all you see is a line, right? So in 2D, it's a line. But now let's say I could somehow go, okay, well, we're now in space. So I can tilt this and look at it from another perspective. What was that line in 3D? What would it be?
A plane.
Plane, right? And so now imagine, right? This is where I think it gets fun, because now imagine like a sine curve, right? So we've been looking at these sine curves, and now imagine that in 3D, right? So it's that same shape that keeps doing this, but it's an entire surface now, right? Because we're sort of opening up. What would that be, right, if we had another dimension?
Kind of like a skateboard park.
Yes.
I was thinking like a surfboard, riding the waves. Now it
Yep,
becomes a lot more fun.
it does. Because that has to be, and one of the things that we can do to help our students to see that is that, right, whatever we're saying is true on the plane. So if y equals x in this plane, well, if I'm looking at all the planes, y has to equal x in every single one of those planes, right? And so now I'm going to stack those up for every single plane, and that's why it continues on the way that it does. Now we're going to look at shapes that may be defined right differently. So we're going to see that there's 3 variables, and so it may not be that y equals x for every single plane. We might see something different. But when we look at those things in 2D and we say, now consider this in 3D, one of the things that we can do is say, okay, that is defined the same in every plane that's stacked up. And that's what gives us that idea of those things continuing on. So how many people feel like they really mastered 2D and are really comfortable there? Right. So do you think things get harder or easier for us to imagine and represent when we add another variable?
Much harder. For me, anyway.
So as we look at our picture of flowers, right? So if you asked me to draw a flower, and I know some of you are artists, right? But if you said to me, draw a flower, I'm going to give you the 2 examples, right, that I would probably try. Let me turn the pen on here, right? Is, right, you would get, there's one of my flowers, right? And we all know it's a flower, but does it really look like those flowers? No, right? Or I'm really good at drawing tulips, right? Or you might say, try really hard and see if you can draw a rose, right? And I might go, okay, I know you have to somehow layer the things, right? And so again, right? Those are my artistic endeavors, right? And those are hard enough in 2D, right? When we look at the artwork, right? What are some of the things that led us, that some of the techniques that the artist may have used to take this attempt to communicate something in 2D and now communicate it in 3D that that adds depth to the picture?
Shading, I think.
Lights and shadows, like white colors versus shadowy dark colors.
Good. Yeah, so both of you, when you talk about those shadows and that shading, we're thinking that there's a light source somewhere, right? So I did pay attention to my kids' art classes, right? That there's some kind of a light source there that's external to this piece, right? This 2D image. There's something else that talks about that 3D world that they live in. What's something else that we see in drawings of 3 dimensions?
Perspective with distance.
Yeah,
Yeah.
along with that, I was going to say you can see the one flower is behind the other one. And then this one here on the right is turned around, facing away from us.
Yeah. So my attempts, right, do not have perspective or shading or layering, but we see that the artist does, right? So when we think about 3 dimensions, right, those are all parts of that third dimension, right? That I'm not just looking at a slice anymore, but I'm looking at the fullness of those 3 dimensions that we live in. Anybody have anything else they'd like to say about the art? I will just
This
mention
is
that
very
this,
different from the pointillism we saw very early on, where it seemed like each individual dot was its own color, and you're getting lots of different tints and hues with these colors. It's like you can slide them along the scale now because all the planes are connected instead of it being flat.
I like that. I will mention that this is an Asian artist. I'm not going to say much more than that because I don't want to speak wrongly. But I did want to point out that when we chose the art, we really were trying to be intentional in choosing art that was representative of different cultures, different eras, different art styles. And so this is um, getting away from, right, it's sometimes easy to stick with those um, sort of European Renaissance artists, and we really tried to break out of that. And so this is one example where we intentionally went and looked for some art from another place. All right, so let's go ahead and jump into our I squared page, our invention page. And I'm going to change my first question for you just a little bit. And I'm going to ask you to use what you know about 1D and 2D. You can use what you know about 0D also if you want to, but thinking of 0D, 1D, and 2D, especially any patterns that you notice, what might you know about 3D, or what might you expect about 3D?
The word that keeps coming to mind is precision. Like as we get more complicated, is there more precision or
Okay,
exactness?
that's an interesting question. If we're trying to describe a location, perhaps, right, as we add in um, more information and we think about dimensions as being, another piece of information, certainly, right? Just if you think about our location on the Earth, if you give me my latitude, you would know where I was north or south of the equator. If you then added longitude, you would know pretty close to where I was. But then if you chose to give me an altitude, you'd know exactly where I was and right on the earth.
I guess that's somewhat what I was going to say. I don't think they can hear.
Yeah, can hear.
Which was that, you know, with 0D, we had no measurement. With 1D, we had one measurement. But in 2D, we then had area. And in 3D, we'll now have volume.
Good. And I want to encourage you, right? Just as we would encourage our students to think about things that are the obvious patterns as well, right? So, as well as saying what our dimensional measure is, area and volume, we could also say there was no measures in 0D, one measures in 1D, right? One linear measure. How many linear measures in 2D? Two. Right? Three linear measures in 3D. So that pattern is going to be true for a lot of things, right? We could talk about the number of axes. So how many axes would we expect there to be, or the number of coordinates in 3D?
3.
Three, right? How about how many directions would we have in 3D? If we had 2 directions in 1D and 4 directions in 2D, how many directions would we have in 3D?
3.
Okay, so hang on, remember directions. So 2 in 2D, sorry, 2 in 1D, 4
Oh,
and
6,
some
yeah.
6 and right.
Mhm.
So encourage your students when you're talking through this, like that is really meaningful if they go, okay, right, how many variables did I work with in 1D? Right? How many variables did I work with in 2D? Now, how many variables will I work with in 3D? So even before we enter into the lesson, right, if we can go back and see some of the patterns that we've been building between the dimensions, there's a lot of things that we already know about 3D before we actually even get there. So as we look at this page, let's look at one thing that might be fun to define. How about octant? Anybody want to take a stab at defining an octant using the middle piece of the page there, that image?
I feel like it's something to do with 8.
Good. So
Just
there's
analogous to a quartile in 2D, like 1/8 of that cube.
yeah, so good. So we had quadrants in 2D because we saw our plane divided into 4, right? And so now we take that 4-ness, right? But now we're going to take that plane and say, okay, we divided our plane into 4, but hey, gosh, look at this. Now that we expand that into space, there's going to be sort of 4 on the bottom and 4 on the top, and we're going to have 8. So we see that octant relating to 8, and we've related it to quadrant, and we see how our axes are going to divide our space into 8 regions. And we don't do this when we get to 4D, but any guesses, if we were to look at this in 4D, how many divisions would there be in 4D?
16.
16.
16.
Yeah.
So now think about this. We have in 1D, right? Our line, if we had the origin, how many parts would we have?
2.
2. And then in 2D, we had 4. In 3D, we have 8. In 4D, we're saying we think we'd have 16. Does anybody see arithmetically what the progression might be?
I was going to say squares, but
Log.
then the first one is a double.
So we're doubling each time, which, so what, anybody know what pattern would give us a double each time? What kind of sequence?
Did we call that an exponential sequence?
Yeah, so it could be a geometric sequence because we're multiplying by 2, but we could also express that exponentially because I could say it's 2 is my base, and then my dimension number would be my index, right? So if we had the 5th dimension, and if this pattern would hold in the 5th dimension, we'd have 2 to the 5th, 3,
32.
which would be 32. So it's kind of, I always think it's kind of interesting because when we look at this mathematically, right, there's octants, but if you watch like Star Trek, right, they're always off in different quadrants. And I'm like, do they know what words they're using? Are there really just 4 quadrants? I don't know. I think there's more, right? Because I think they talk about the gamma quadrant. And I'm like, but there's only 4. So you can't really have the gamma, right? After alpha, beta, and so forth. So yes, we won't poke any more holes into the Star Trek universe today. But
That's your next gig. You're their math consultant.
What are you
I
working
would
on,
love
Naomi?
that. That would be fun. All
Yeah.
right.
I saw you doing some lab cards a minute ago.
So let's take a look here. Here's another one I want to challenge you to look at. I want you to look at the bottom row that says lines on 3D cubes. And is there a relationship between those lines that is new to you?
Well, the
Skew.
word that came out to me was skew, but we saw it. It was in the charts week 17. Like I'm on 17 this week. And so I saw skew and I highlighted it, but I'm like, this is something unfamiliar.
Yeah, so skew really is a 3rd dimension idea because if I have, so coincident lines, could I have coincident lines in 1D?
No. 1D, yes.
Yes, right, because they're the same. So I could have coincident lines in 1D. Could I have parallel lines in 1D?
No.
No. So I know that my parallel lines are going to require that I'm at least in 2 dimensions. How about intersecting or perpendicular lines? They have to be in 2D, right? But as soon as I have skew lines, what I'm saying is that I have 2 lines that don't intersect, right? So that perpendicular represents all intersecting lines. If they don't intersect, but they're not parallel, right? Can that happen in 2D?
No.
No, it can only happen in 3D, right? That I've got 2 intersecting lines that are also not parallel. So that's a new relationship that we're going to see. So again, we can talk about how these things happen either by their circumstance of dimension, right? Or the relationship that's happening between those lines.
Let me
Did you
just
mean to
ask a
say 2 non-intersecting lines? Or
She
did you mean you can't have 2 intersecting lines that are not parallel?
In 2D, my lines either intersect or they're parallel. In 3D, if they intersect, they have to be in 2D. So if they're not intersecting and they're not parallel, that's what skew is. And that can only happen in 3D or higher dimensions.
because they'd be on a different plane,
They would
right?
be on
Because if they're
different
on the
planes.
same plane at some point, they're going to intersect if they're not parallel.
Exactly. All right, let's take a look at our Memoria and arrangement page. And this page has a lot to do with arrangement, but let's go ahead and start by looking at the bottom of the page. What are some things that we could name on the bottom of the page?
like the dimension names themselves?
Sure.
So many
And
variables.
The
Shape of
shapes.
the solution is pretty important.
Yeah. So we could name the shape of the solution, right? And it's given to us there, right? That this is the line, goes with the line, right? The point right there. Here's our point. So helping students to connect the image and then the shape of the solution and naming that, I think is something that we can help them to do on this page. If you have younger students, right? So one of the big ideas on this page is the idea of intersection. How could you, with younger students, express intersection?
I think of little kids with their toy cars and driving their cars, and you can explain, like follow this line and follow this line and what happens with the cars.
Good. Yeah. Do we want to have two cars that intersect?
You could do yarn and have two kids, or if you have four people total, holding yarn and trying to be parallel and trying to intersect and trying to be skew.
Well, I like that. I was thinking about holding hands, right? Where you hold hands, is that the intersection of two people? If you have kids that are maybe not so touchy-feely, you could have their stuffed animals hold hands, right? So even for our younger students, right, just talking about that idea of intersection being a point that's shared, right, by two figures. So we looked at that in 17. Right. So somebody just said they were in 17 looking at intersections. So now we're going to look at, well, what if I have 3D, right? What if there are three different things that I have intersecting? So one of the things I really want to attend to on this page are the number of unknowns, right? Like the number of equations and the number of unknowns. And so we look at that at the top where we say we have three equations with three unknowns, but we're also looking at that at the bottom where we see this table laid out where I have one unknown and one equation in 1D. In 2D, I might have two unknowns and one or two equations, right? That I can start to see how this builds. And based off of that, like what are my possible solutions as I work through that? Does it get harder or easier to find a single point of intersection between all of my pieces if I have more or less? Like, is it going to get harder as I get more pieces or easier?
Harder.
Harder, right? And how could we let kids discover that? Just drawing lines on a paper, right? Like if I draw two lines, I'm almost guaranteed that I can make the two lines intersect. But once I have those two intersections, right, drawing that next one so it intersects perfectly, that's usually a little bit harder, right? Then you try another one and it gets even harder, right? And so the more lines I'm trying to get, right, my hand jiggles. So just exploring that with your students, right, I think is maybe valuable in helping them see, right? So if I look at a plane, if I have two planes that are not parallel, right, I can find their intersection. Well, then put another one in, right? And I'm going to find one point. And then, right, I keep doing this and keep coming up with weird things so that I see that it's hard to get one point of intersection. And then this top section, I'm going to tell you, right, this is challenging. This is a big math idea that's challenging. And so what I would do here, even with my younger challenge students, right, is to talk about narrating the process of finding a solution, right? And how could they narrate the process of finding a solution on this page?
Just reading what's beside the number, like given 3 planes, like just reading the directions?
Just reading the directions, right? So I can read the directions and that allows me to narrate what's going on, right? And that's a skill, right? Just being able to follow in order, 1, 2, 3, 4, 5, 6, 7, reading that in order to narrate what's going on. Does anybody see anything else on this page that they'd like to?
Can you exemplify what you mean by that? Can you do that narration as if you are a challenge A student that we just asked that?
Sure. So if I was just reading this with my student, I'd say, okay, well, what's first, right? And I'd have them say, given 3 planes. Okay, well, what are the 3 planes? Whether they pointed them out or just said, these are the 3 planes, right? So, okay, so here's 3 equations. And so we're going to assume that those are my 3 planes. Good. What's the next step? So then I would want them to look and go, okay, the second step is to solve equation A and or B and subtract to eliminate X. Okay, so not going to worry too much about this, but I might come down and say, okay, does it look like I'm adding or subtracting? Well, I'm subtracting. Okay, good. So I have A and here's B and I'm subtracting and I got something else, right? All right, what next? Well, step 3 is to solve equation B and or sorry, scale equations B and or C and subtract to eliminate X. Okay, does that sound like something else? Well, it sounds like step 2, but now I'm using 2 different equations, right? Okay, so B is still from my original. C is a new one. That's a different one to what I used in step 2. And so now I've got E. I've got like another equation, right? It's starting to feel overwhelming because there's all these different equations. Well, that's okay. Let's go ahead and look at step 4. Well, step 4 says to scale equations D and or E and subtract. So I keep doing the same thing just with different equations. So now I see, where did D come from? Oh, D's over here. Where did E come from? E's right here. Did I add or subtract? I subtracted. Okay. And here it says solve for Y. Is there something that says solve for Y, like Y equals? Yep, it's right here. Y equals 2. All right, what's the next step? The next step is 5. Substitute Y into E and solve for Z. Okay, so what do they mean? Well, Y was 2. Okay, what do you think they mean by E? Well, before it was always an equation. Okay, does it look like it's an equation here? Well, it looks a little bit different, right? Because here I got rid of my Y already, but the 2's look like they're the same. So I think this is the same equation as above. It is. So when we solve this, what does Z have to be, right? And I'm not even worrying about the work, but oh, here Z is 3. All right, what's the next step? Well, the next step says to substitute Y and Z in A to solve for X. Okay, so what happened when they did that? Well, they found out that X was 2. Okay, now it says substitute X, Y, and Z into B and C to verify. So can you find X? Yep, it was 2. What about Y? Y was 2. How about Z? Z was 3. So when I substitute that back into these equations, did my equations end up true? Yep, 11 does equal 11 and 13 does equal 13. So that solution must be correct. So that's what I would do. I wouldn't even really be trying. I would just be asking them, not so much to understand what they were doing, but to pull out some words like add or subtract. Right? Can you read what their last statement was? And that's all I would do, Nicole. I wouldn't even really be trying to explain it, but just can you read the next step and then pull out
Okay.
something from it?
And can you just tell me one more thing? How would you explain the word scale? When it says scale equations, it just means we're just stacking them?
So scale means, so that goes, I know it's a word we use and we maybe haven't used it quite in this context, but we have used it. So we could go back to lesson 5. And in lesson 5, we talk about how multiplication gives us a scale, right? We're scaling things, especially when we looked at vectors, we would have a scale factor. When we In 18, just last week, we talked about scale factors, and they were always numbers that were being used as a factor, right? We could relate it to our idea of when we talked about scalar versus vector, that a scale to scale something is just to multiply it by a constant. It's just making it bigger or smaller by multiplying it by a constant. And so when we scale an equation, we're multiplying the entire equation by the same constant. So every term on both sides of the equal sign is being multiplied by the same number.
And that's with that -3 in front of the B and the -1 in front of the C. That's what that is.
Yes.
Okay.
And is the purpose always to have at least one or one of the variables have the same coefficient? I mean, is it a fair way to explain that?
So that's when we have three variables, our goal is to systematically eliminate a variable so that I end up with one variable, because then I can solve the equation for that one variable, and then I work backwards to find out the other values. Right. Now,
and has that concept already been covered? I missed a couple of weeks in here, so has that concept already been delved into, if that's a word, or is that something we're observing here that we'll pull out later?
So you're going to, if you went back and looked at lesson 10, that's the first time we talked about intersections. And we did that by setting, if I had two equations like y equals x plus 3 and y equals 2x minus 1, we would say, okay, if both of those are equal to y, I can set them equal to each other. Eliminated y, right? So that I would only have one variable. In lesson 17, we looked at taking those equations and using what we call a simultaneous equation or elimination method, so that we looked at other ways of solving those two variable systems. Now we're extending this to a three variable system. It's the same idea. You just have to eliminate one variable at a time. We do want to emphasize, right, that this is, remember, this page is the same for all of our domains. This is not something that we expect any complex student to be able to do. The big idea when it comes to intersections is that if I have a point that is an intersection, it's going to make all of those equations true, right? So if the point 2, 2, 3 is the intersection of these three lines, then that point has to make all of those equations true. And I think students at this level, right now, take in mind, right, we've got a wide range of students, so not every student, but I think a lot of students at this level should be able to take those points and substitute them in and simplify to get the numbers. And so that would be the big idea that we're saying here, is that if I have a point that's a solution, then all of those equations true. That's where I go back to that idea of storytelling, and narration can just be reading. Can you read these in order the way they go?
Okay, one more question.
Yep.
Because one of the concerns that continues to come up is around confidence. So can you give me an idea of like how and when do you, I know you can't guarantee or even predict, but like, do you expect that these types of more complex big ideas will the student will be expected to understand them?
Sure. So I would say solving simultaneous equations, right? Especially, I would say probably in binomials, I would think a student should start becoming confident with solving through substitution. So if I have, for example, two-dimensional equations, and I'm just going to write these right so that you can see what I mean. So like a y equals x plus 3 and y equals 2x minus 1. I would say in binomials, they should start being comfortable with either saying that I can take some expression for y and substitute it in, or setting the two equal to each other, right? So being able to do this should start to feel familiar in binomials. In polynomials, the following year, I would say maybe then they start to become a little bit more comfortable with something like this and going, okay, well, if I multiply this top one by -2, then I'm going to have -2y, -2x, and -6, and I can add those together. And on this side, I have -y equals 0, minus 7, and y equals 7. So I think in polynomials, I would expect a student to be pretty comfortable with, again, looking at two-dimensional simultaneous equations. And then in their expressions or transcendentals year, that then they should be able to take what they've done here and say, okay, well, I can use this now to look at three-dimensional equations or equations with 3 variables.
Okay. And you said transcendentals, is that 12th grade?
That's our, that would be the final year.
Okay. Thank you.
You're welcome. All right. So let's go ahead and take a look at our charts. And I have not been doing a very good job of keeping track of our time. So we spent a lot of time on those 2 pages, but I think it was good time. I'm not going to talk much about chart 1 because we kind of covered some of the ideas on our I2 page, our I squared page. So let's take a look here at the right-hand side. And does anybody have anything? Take a look at that. Anybody have anything that they would like to comment about what might be familiar or unfamiliar on chart 2?
I see that some of the same equations are in place. We've just added another letter. And I see that we continue to use vectors that we've become friends with throughout the year.
Good. So yeah, so we see that progression at the top there. We're adding a variable. And so the perhaps now familiar equations, especially if we've been doing this a couple of years, we see, oh, this is just growing, right? That we see that's growing. What might be significant about our vectors in 3D? How many coordinates do our 3D vectors have?
They have 3 now.
They have 3 now, yeah. So our 3D vectors are going to have 3 coordinates. And so that goes back to our pattern, right? How many coordinates does a 1D vector have? 1. How many coordinates does a 2D vector have?
2.
2. How many coordinates does a 3D vector have?
3.
3. How many coordinates would a 4D vector have?
4.
4. So here's the really cool thing about vectors is that if I understand operations on vectors, right? So if I know how to add 2 vectors together, right? Is there anybody that says, oh, I feel pretty confident? What do you do to add 2 vectors together?
Hey, Nicole, can you mute?
You just add them end to end.
We add them end to end, right? And we end up adding our x coordinates together in 1D, or if it was in 2D, I'd had my x's together and I had my y's together, right? that I just match up my coordinates and I add them. So once I understand how to add them, what if I had a 100-dimensional vector? Could I add my 100-dimensional vectors together?
Yeah, you just X's together, Y's together, Z's together.
Yep, I would just add each of my coordinates, right? So to me, this is one of the really powerful things about vectors is that when I start to become familiar with how to operate with a vector, it doesn't really matter how many coordinates it has. I just do the thing to the coordinates, right? So if I was going to scale it, I just scale each coordinate. So one of the things that we're going to learn here is that one of our most common open shapes, one of the things that we are maybe the most familiar with by this point is our line, right? How many points determine a line?
2.
Right? And really, that doesn't matter if I'm in 1D, right? There's only one line, but I could take any 2 points and say, this is the line. In 2D, 2 points, there's only one line that goes through those 2 points. How about 3D? How many lines can go through 2 points? Just one. But let's think back to what I talked about. If I say y equals x, right, and I'm in my plane, remember we said it looks like a line in the plane. But if I just say y equals x and I'm in 3D, is it a line? It's
a plane.
It's a plane, right? And we're going to find out that if I just added z, so a lot of us think, well, I'll just add z, x plus y plus z. Well, actually, it doesn't. It just defines a specific plane, right? It says, okay, I'm going to change my plane a little bit and talk about x plus y plus z. That linear equation defines a plane in 3D. And so we need another way to talk about lines. And we're going to discover that we're going to use vector equations to talk about the equation of a line, not just in 3D, but 4D and 100D. That once we can sit here, and I'm not going to lie, you're going to wrestle with this for probably a couple of years before you start to like believe me. But once you wrestle with it and you get to the point where you like, okay, I understand how they're using a vector to define a line in space, that same definition will work for any dimension. Because what we're going to say is that from my origin, right, whatever my origin is, I'm going to say I'm going to use one vector to identify a point, right? And in 2D, we talk about slope, right? We say, okay, well, from that point, I can find my slope to get to another point. Well, what we're going to do is we're going to say, here's my point in 3D, and then I'm going to use a vector to describe my direction from that point to the next point. The slope, it's kind of like a vector. It's not really. I don't want you to confuse it because it's right, but it kind of gives us that same idea, right? It gives us a change in y and a change in x. So we could write it as a direction vector, telling us what direction to go in for our next point. In 3D, I need to have 3 different changes, right? And I can't do that with a fraction because there's just a numerator and a denominator. So I need to say, okay, instead of just your change in y and your change in x, I need to say, okay, I'm going to go up 1, left 1, back 1, right? To get my next point. And so now I've got this point and I've got this point, and the line that goes through them, which happens to go along our direction vector, is our line in 3D. And so that's what we're doing here is in 2D, right? My slope gives me my change in x and my change in y. In 3D, I need a change in x, a change in y, and a change in z, which is why I use vectors to communicate all 3 pieces of information, right? And so that same equation is going to work for any of our dimensions, which is really cool, right? Isn't that neat that there's not like a different way to express a line in each dimension, but there's one way that works for all dimensions? So I get excited about this. This is actually something I've learned like through my work on the math map, because right, Lee was the one that was like, we really need to understand vectors. And then I started understanding vectors and I was like, oh, this is so cool. This is really, really neat stuff, because I just have to understand it once and it's going to work for any dimension. So anyway, that's like a really big idea this week, right? That we can't just use y equals mx plus b in 3D, because I have 3 variables now. I have to do things differently. But once I start wrestling with this again over the course of a couple of years, as we wrestle through this, we're going to see that what we learn here is going to apply to every possible dimension.
So would it replace y equals mx plus b?
It can. So in 2D, it's easy to work with y equals mx plus b. But I can, right? I could take, let me just write, if I had y equals 4x plus 3, right? I could say, if this is my vector, that some vector p, and my starting point here would be 0, 3. And then instead of using x, we use what we call as a parameter, just a counting variable. So it doesn't necessarily, it's not a variable that I'm comparing in my equation. It's just saying how many counts of my direction vector would I need. So I would say, I would use t, and then I would say for every t, right, each step, this is the same as 1 in the x direction, 4 in the y direction. So I can write vector equation in 2D, and we can write it in 1D, which actually helps us to understand arithmetic differently, but we won't go there today. But this is still more familiar, and it's still easier because this actually relates my x and my y together in 2D. But once we get to 3D, you'll notice as you work through this, we're going to talk about parametric equations where there's we have an equation for x, an equation for y, and an equation for z that are all in terms of a third variable, that parameter. But these vector equations put those together into one. So.
Okay, thank
No,
you. Can I ask one more question?
Yep.
I'm sorry. I heard you say, Lee says we really need to understand vectors. I'm still struggling to understand vectors, and I'm okay with struggling. I'll struggle again, and I'm sure I'll get it in a year or 2 or 5 or 8 or whatever. But because I have that many years to go with these kids. But my question is, why do we need to understand vectors again?
Sure. So there's 2 reasons. One, I think Lee came at it from an engineering perspective, right? And physics and engineering is a lot of studies of things like force and torque, and right, those kinds of things are all what we call vector quantities because they have a magnitude and they have a direction, right? So if I'm thinking about force, if I have a force of 5 pounds per square inch, well, the direction matters, right? Is it pushing me up? Is it pushing me down? Is it pushing me left? Right? So it's important for students who are going to be studying physics or any kind of engineering, understanding vectors is going to really help them to keep track of all of those different things. Any student who wants to go on in mathematics, right, as we're pointing out here, vectors allow us to talk about all of these different dimensions without having to have these equations with all these different variables, right? I can say this equation right? That any point on my line is some initial point plus some counter times a direction vector is true for any dimension. And so as we start to study things that become with all these extra dimensions that we're looking at, vectors are going to give us a way to be able to talk about those ideas without having, 14 variables that we're trying to define for each of those dimensions. Instead, I can use these vectors to give me some things that are true about all of those things. So in those ways, I think Lee was pushing to really help students become familiar with vectors because they're going to be an entree into some of those more advanced realms of mathematics, right? Not necessarily the calculus realm of things, although you may see them there, but those big ideas where you're thinking, right, broadly about mathematics and other dimensions, vectors are going to be an entree into those conversations.
Can I just say, I'm so excited that we have those kinds of high level advanced thinking made available for kids who might not ever have crossed paths with it any other way. And they don't have to understand it all, but they will know it's there. They'll understand some of the concepts, and I'm sure that they will find some nuggets there that they feel equipped, that if they wanted to pursue math, it's not that they can't, it's that they maybe don't want to for their career.
Yeah, and Jill, these ideas are right. So just imagine this. So if you wanted to make some things fun for your kids, right, you could do 10th dimension addition, right? So I'm just going to go here. So let's say you wanted to make things fun for your kids. You could say, okay, we're going to do 10th dimension addition today. And I'm just going to, right, and you could, and I'm just using these numbers here. You could make up whatever numbers you wanted to. Right. And I'm going to give you another one. Right. And I'm just going to add these together. Well, the notation looks weird, but the addition is something that they've been doing all year because all I have to do is 1 plus 3 is 4, 2 plus 6 is 8, 3 plus 9 is 12, right? I don't even have to keep track of place value because I'm just adding those numbers, right? 8 and 24 is 32, 9 and 27 is 36 and 40. Right. So vectors give us this opportunity to sort of play with these different dimensions in ways that are still accessible to all of our students. And you may not get that this year. Like, I really want to encourage us all that this is just a glimpse of where we're headed in the years to come as we all gain familiarity and confidence. So I know we're close on time, so I'm going to just very briefly address, as you look at the tops of your pages, there's going to be a lot of looking at 2D compared to 3D. Notice we're plotting points, and we're looking here. So point 1 is at 0, 0. This is a review. Point 2 is at 2, 3. And then looking at that in 3 dimensions, right? We now have 0, 0, 0 is 0.1. Now I have 2 in my X, 2 in my X. I have 3 in my Y, and I have 4 in my Z to get to my 0.2, right? And so there's a lot of help there to help the students locate those points, because now we are starting to use perspective. It is it's hard, right? Taking 3 dimensions onto 2 dimensions is hard. And so we're just doing the best we can to help our students to start thinking about
Do we lose Kirsty?
Yeah, she's frozen. We'll give her a second. He might rejoin. So let's just give her a couple more minutes.
Okay.
I'll ask a question if you don't mind. If anybody already knows the answer to it, you can tell me. When we do the two-dimensional plane and we have the quadrants 1, 2, 3, and 4 going counterclockwise, and then we move into the three-dimensional, the labels, the 1, 2, 3, and 4, are that just the face of the, cube, or is that the volume of the cube that we're labeling? It's that whole voluminous section. That's like quadrant one. Quadrant one would be the whole three-dimensional volume of that, like top half of that cube or
That's my
whatever.
understanding.
Yeah, Babs, correct me if I'm wrong, but I think it would almost be like if you had 8 clear boxes
Mhm.
that you could look at and recognize. Like you did 4 flat pieces of paper on a grid, you could see the 4 quadrants and that they're flat. But then if you did 8 clear boxes, you'd have 8 on the top of the XY, and I mean 4 on the top of the XY and 4 on the bottom. So it's almost like you took your trivium table and laid it in between 4 boxes and 4 boxes, and your XY is here in the middle.
Mm-hmm.
Gotcha. So quadrant one is like the top cube, the top quarter of the cube, and quadrant 5 is like the bottom quarter of the cube. The bottom, well, no, not
And
bottom,
it's
but like
labeled on the chart too. So if you
that's what,
look
yeah, but I'm
at
trying to,
chart one,
I'm looking at
yeah.
this chart and I'm like, if you look at it different ways, it's like, which way is this line going? Like,
Didn't you
that's
do a
what I'm trying
little
to figure out.
hands thing, Bab, where you did like feet and kicks and hands? Oh, there's Kirsty.
So I was going to say, I do have a video on CC Connected on the companion where I actually use my body. So if you use your body as your Z axis and your arms as your X and Y axis, then you can sort of go, okay, this is octant 1. And so it's hard to hold the phone and do this because my internet apparently has gone down. So I'm on my phone. But I would suggest going and looking at that because that may help you. And the other thing that's helpful is if you have a tissue box. A tissue box can be really helpful in picturing 3 dimensions and being able to look and say, okay, in this box, this is where the first quadrant would be. Right. Like I have a box and I have to draw like my Y and my X and Z on that.
I think she's frozen again, this time with the box in her hand. I think the video she's talking about is when you go into the companion and you're on the math map page, you click on the booklet titles themselves. And if you click on open shapes, there's 2 videos, and the top video is her and she's talking through that.
Okay, great. That's helpful. I'll watch it. But I think the answer to my question is that quadrant 1 is not labeling the face of the quadrant, it's labeling the entire volume of that quadrant, right?
Mm-hmm.
Okay. All
Nicole,
right.
I think it may help you to know that I noticed that she said octant. So in
Uh-huh.
2D, you have quadrants, and in 4D, you have octants.
Oh, yes.
Yes, that
So
is
octant.
exactly right, Melba. Mm-hmm.
Okay. So the octant is the whole the entire area or volume of that space. Got it.
Mm-hmm.
Okay, that's helpful. I don't know. Because it's time to go.
There was a lot in this lesson. I thought it's a lot. Yeah, I was chatting with someone a while ago. There are some very deep questions that I did not understand. So I'm going to be the first to admit that there are some things I probably won't get to discuss that she talked about in my class.
Mhm.
I'm not there
Mhm.
yet. So, and I don't know what year this is on, Jill, but I think it's still okay that we're not completely at that point, which is good. Why, you know, we're classical learners, right? So we need that repetition. We need to hear it over and over again. Come back and watch this video over and over again.
Yeah. And I was talking this morning to a you know, group of SRs who are trying to figure out the, you know, the I don't know, they're trying to figure out binomial sales, basically, how to get, like, are we trying to get people on board for the Math Map for Challenge B, and they're having such a hard time with these things. And I guess what I'm trying to get to is it's a trust fall. Like, we're trusting that this is going to happen, right? Like that we're going to, it's just like essentials in the beginning, right? Like we just didn't get it that first time through. And I know, but I think it's okay that it's a trust fall. We just acknowledge that. And
Well,
that is,
here's an example. So I saw there was I think she was a parent, and I don't know if her student was in Challenge A or if she was like Essentials age, but she's just doing the flashcards. She was going through the flashcards, and she came across something, and the daughter, and she like told her mom, well, this is what this means, da 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 da. And her mom was like, well, how'd you get that? Because that's not on the card. She's like, I don't know, I just got it. Well, her mom's like, I didn't tell her. You know, so it's just like, you know, every kid's going to get to that point at their own time, right? And it, just like we were just talking about, I didn't get some of that was discussed today. Like I just didn't. So maybe the next round, maybe not, but maybe I'm not going to be getting to that point. But I think that's the beauty of a curriculum that allows you to glean what you can. On a call earlier today, we were talking to some team leaders, and we're talking about how, you know, there's some, you are going to have some students who are not interested in knowing more, right? They don't care. They don't want to. But you're also going to have this set of kids who now sees all of this, that they want to go further. Well, with another curriculum, they're just learning what's in that particular chapter. But now, as a student, I see, wow, all this is available to me. And if I want to go further, you know, I can. So I don't know, just another perspective, you know, to kind of talk through.
that's really good.
Yeah, honest about what you don't know, for sure. Well, I don't know that Kirsty's coming back, so I don't mind staying and answering questions about logistics, and I'm sure Shauna wouldn't mind answering them, or Jill. We probably don't want to answer math questions. So if anybody has any logistical questions they want to ask, we'll be glad to try to answer them. Otherwise, we'll close out the call.
I have a quick question.
Sure.
We just finished lesson 16 in community yesterday. It was our first week back. And, you know, as I think every campus does, we do an end of year celebration, you know, end of year, where the foundation's kids recite things, essentials, and challenge kids show, you know, what they know to the parents. And our challenge 3 director and I were texting back and forth because she was struggling with some unit circles. And I said, oh my gosh, I am so excited for learning these unit circles. And we were on this thread making, you know, seeing some patterns and whatnot. Anyway, I went on YouTube because I don't know if it was Jill or Jana who had mentioned in that math map video about the hand motions, you know, the arm motions. And I didn't know if someone could share that, post it, because I think it would be amazing for my Challenge A kiddos to learn that and be able to do that for their end of year, show what they've learned.
I think that was Jana.
That's what I thought. And I see she's not on here any longer. So I tried looking her up on Facebook, but I couldn't find her.
I can reach out to Jana and ask her and post it somewhere. So is it a video about the unit circle and just using motions?
Yeah, I thought she said she had hand motions, like arm motions, like 0, 30, pi over 6, 45, pi over 4. Am I doing
Okay.
that right? And and so on. So I just thought, oh, that would be so much fun.
Okay.
Mhm.
Yeah. So I wrote your name down, and then I'll reach out to Jana because she's emailed the math map before. So we have her email address. So I'll reach
I
out
would
to her and ask
definitely
her
like
if she
that
has
video
it.
too.
Okay.
Yeah, and I just checked the MathMap Facebook page, scrolling through to see if maybe someone had linked some sort of video there, and I haven't seen that either.
I think on
So
the actual book club video, we talked about a hand having the different things.
yeah, I
but
saw
it
the
wasn't
picture of the hand,
mhm.
but I thought Jana
Maybe
said there's a motion,
Okay.
kind of like how we do our hand motions and foundations.
Or maybe
Super.
post it
Thank
in
you so much,
when you
Babs.
whoever does, if you get it, just post it in the group on Facebook, and we'll all have it.
All right. We'll look for it.
Thank you.
All right. Well, thank you guys for coming today. We're going to go ahead and close out the call. And hopefully Kirsty is getting her internet back together. We all know how that can be. And then we will see you next week. Thank you guys for coming.
Thank you.